Good morning, everyone. My name is Jared O'Neill. I'm a scientific software developer at Argonne. And over the next 40 minutes or so, we're going to be talking about something called requirements, which is heavily related to what Catherine was just talking about in many different ways. And so when we say requirements, we mean specifically in the context of a design process. And then we'll end up with a brief introduction to test-driven development, as well as an exercise of what that might look like. And so I want to thank Jim, who's here today and who's going to be presenting as well, and also Reed Milowitz. So these are colleagues of mine on the Ideas Productivity Project, and they've helped me improve my understanding of requirements and also compose to some degree the content of this talk. And so when we go through our daily lives, of course, we come across and use the word requirements on quite often, and of course we have a good understanding of what we mean by that word. But when we talk about a design process or designing software, oftentimes we're using that word in an overloaded sense. In other words, we're extending that original colloquial meaning and using it in a bit more of a formal way, heavily rooted in design. And so we'll start off this talk by coming up with an informal definition of what we mean by requirements. And so for me, requirements are a complete set of statements that are all well-defined and mutually consistent. And the reason we write these down is because we want to express what it is that we want to build or what it is that we're trying to achieve. And we're also going to package up those requirements with some statements about why we believe that those requirements are actually important. And so this definition, as it starts off, is always already a little bit problematic because we have this word complete in there. And as we can all imagine, trying to strive for something like a complete description of what we want to do in terms of statements is probably not achievable, nor something that we should try to achieve. And so as we go through this talk, hopefully we'll come up what it means for a team to decide what it means to have a sufficiently complete collection of requirements. So these terms, though, that we want well-defined and mutually consistent, hopefully those are targets that we actually can achieve through this particular process. So requirements, what they're really about for me is really getting to a common understanding of what it is that we want to do. What are we trying to build before we jump off and get too deep into the process of trying to figure out how we want to build it. That should hopefully make some sense. We don't want to get too down the path where we've spent a lot of time and effort to build something and then find out that it doesn't actually do what we need it to do, or it's going to be really hard to try to retool it to get it to do what we need it to do. Something that's not clear from this definition, but that's also important, is that we need each and every one of those statements to actually be verifiable. We're going to spend time thinking about requirements, writing them down, and if at the end, after I've used those to build software, I can't actually determine that those requirements have actually been satisfied by what I've done, then I've just wasted time in trying to write those down, and I've injected noise into the design process. So verifiability should be quite important, and as also we heard about already in the morning, we want those to be documented in one way or another. So there are different ways for us to classify requirements. One of the main ones is to call them either functional or non-functional. So a functional requirement is a requirement that communicates what services should or should not be provided. This should include, for instance, what type of inputs they take, how they react to those inputs. If our software can be put into different states, we want to describe what those states are and what the behavior is of the software in those states. And we might oftentimes come across the point where we have corner or edge cases. So we would like to describe what those edge cases are, how the software behaves, and the outputs that it gives once it's put into those situations. So an example of a functional requirement is the statement, a new feature shall be added to the software such that simulation Z can be configured at runtime to use a lower order but more performance solver. So we're talking here about these particular simulation Z, and we would like the software to do this service in terms of giving us a solution. So that certainly sounds functional to me. And we can start to try to evaluate whether or not we really think that this is a good requirement. So I don't see anything in this statement that's particularly inconsistent in and of itself. However, I'm going to raise some questions and say I don't really think having these relative terms like lower order or more performant are actually well defined. So I can give you an example. We might spend 6 months trying to come up with this solver, and then when we run it on this simulation that used to take us 24 hours beforehand, now it runs just 5 seconds faster. Well, strictly speaking, we've satisfied this requirement, but certainly we haven't done what we really set out to do. And so in that particular case, maybe we want to put some more effort in to try to figure out what more performant means. And we can also go a little bit deeper with this, because if I come up with some quantitative criteria, how am I going to verify that? Maybe I'll be able to run a few simulations, particular simulations on a few platforms, and be able to verify that in those cases they meet my performance criteria. But if my real goal is to say that in every case it should be performant, that's not necessarily knowable, right? And I might need to rethink a little bit about what I'm working on. So non-functional requirements are those that are going to communicate constraints on the services and functionality of the software. So this could be in terms of portability, in terms of performance. It could also be in terms of our design process, our implementation, and our maintenance process. And so an example of this would be the software shall be developed as an open source project that is hosted on a Git-based version control host and shall have automated testing integrated in the repository for use with continuous integration. And so if you guys are paying attention, you'll see that I have performance here in non-functional, but in this example I put up a functional, I also have it baked in. So in some sense then this example that I gave you here is actually a mixture of both functional and non-functional requirements. So another way to categorize requirements is in terms of their granularity. So we have on one end of the spectrum low-level requirements. These are going to be requirements that are heavily detailed or heavily specified. And that might be something we want to do because either we're going to be placing a lot of heavy constraints on what it is that we're trying to achieve, or maybe someone externally has placed these constraints on us. And so ideally when we're doing these requirements, we don't actually want to inform them whatsoever in terms of implementation details, right? It's what do we want, not how are we going to achieve it. But in some cases, for instance, if I'm working on a project where I don't have much time or I don't have many resources, maybe I'm going to think about implementing my software with one particular library package because that's going to help me accomplish my goals with the resources that I have. And so in that sense, that could be considered something like a constraint. And we have to be a little bit careful about low-level requirements because if we start to use them too much, we're really going to start to pin down the design in a way that might not be desirable. So for instance, by the time we give these low-level requirements to the people who are going to do the design and the implementation, we might have hindered completely their freedom and their creativity so that the solution that they come up with is really subpar and not what we were trying to get when we set out. So an example of a low-level requirement is that the software architecture shall be upgraded such that simulation can be run on nodes with Model X CPUs and Model Y GPUs. And the use of GPUs shall be determined by the preprocessor. So this is fairly specific. We're fixing ourselves to CPUs, GPUs, exact models, and we're going to be using a language with a preprocessor, for example. So on the other end of this aspect, we have high-level requirements. For me, the idea here is that when we're setting out on a project, oftentimes the only thing that we can see are the details, and those details make everything look really difficult, and sometimes they can obfuscate what it is that we're trying to do. So we use high-level requirements to try to abstract away the detail, to make those, push those details aside and really try to get at really the core essence of what it is that we're trying to do. So these are going to be broader ideas, concepts, constraints, and abstractions. One thing that's nice about this is when we push away technical details and hopefully limit the jargon, that these are going to be statements that people from different levels of experience with expertise and different disciplines will be able to understand fairly easily. A reality of what we do, of course, as Catherine mentioned, is that the requirements are constantly changing. So ideally what we would want to do is have these requirements be fairly robust to the change. And if we're able to encapsulate what it is that we're trying to do in terms of these more broad statements, hopefully that will be what we achieve. A problem with high-level requirements, though, is if I only have high-level requirements and I give these to the development and implementation teams and they don't have that necessary domain expertise, then when they come across a design decision, a low-level design decision, it might very well be that what's contained in those high-level requirements is not sufficient for them to be able to make high-quality, low-level decisions. So an example of a high-level requirements, which is an extension of what we saw in the last one, is that the software architecture shall be upgraded such that a simulation can be built to run on a node with only CPUs or on a node with accelerators. We're not fixing ourselves to any particular type of accelerator, any particular models. And so what we're really expressing with this is what we were just talking about. I want to make my software future-proof. I recognize that there are homogeneous nodes and heterogeneous nodes, and I want it to be able to run on either one. So a third class is by internally versus externally exposed, and so hopefully that's fairly simple to understand. And I want to just give you a different flavor of an example of a requirement. So the other ones were a bit more technical in detail. This one is a bit existing at the level of a numerical model. So let's imagine we have a piece of software where we're going to be estimating the first and second derivatives of a function. So we might write the requirement, if a function f is symmetric about 0, then its first derivative is antisymmetric and its second derivative is symmetric. And the routines for numerically estimating these derivatives shall be implemented such that these mathematical properties are also true for estimations. So this seems pretty clear. That's a property I would probably like to have in my numerical implementations. And it's also quite high level. So for instance, I'm not fixing you down. I'm not saying that you have to use any particular algorithm to do this, right? I just want that property carried over. So now what we can do is try to think about how you actually go about arriving at these requirements. So ideally, this shouldn't be just one single lone person suffering at their desk trying to accomplish this. The reason we don't want that is because that person has potentially just one viewpoint of the software and its constraints. And so what we would really like to do is have a number of people involved in this process who represent a completely different set of views, or the total set of viewpoints associated with the software in terms of development, implementation, maintenance, and use, with the idea that together they're going to be able to come up with that really good common understanding of what it is that they want to do, and do so quickly. So for instance, we want to have domain experts because, among other things, they're going to be able to define limits, needs, and tolerances. We want developers and technical experts because they can understand the technical constraints. And we want the users involved so that the interfaces that we end up designing and implementing result in a piece of software that that community can actually use. So now that we understand requirements in some general sense, let's try to move that out to the broader scope of how they fit into a design process. So this is one particular example of how you might structure your design process. So it's fairly formal and heavy. We imagine that we're working on a piece of software that's deficient in some sense. In other words, there's computations that people would like to use it for but can't because, for instance, it doesn't satisfy the precision that they require to do their science and engineering. So we'll get these scientists, this user community, our collaborators together and try to get them to establish what are the computations that they want to do and what are the criteria for success in the form of science and engineering cases. And then we can give those to this team who are going to do the requirements, and we ask them to do something called requirement elicitation, specification, and validation. So elicitation, what that means, it's essentially akin to just brainstorming. We're going to get them to talk, to really try to figure out and flesh out the details about what it is they want to do and what constraints exist. Once they've gotten to a reasonable common understanding, then they can specify those and write those down. And then we can move on to analysis and validation, where we're going to actually ask ourselves, are these statements sufficiently complete? Are they well defined? Are they mutually consistent? And if we give people this set of requirements, will they actually, with a high degree of probability, create the actual software that's needed for the community? And ideally, when they're doing this, they're also going to be upfront designing what are the tests that are needed to actually confirm that all of those requirements are going to be satisfied. So once we have that good specification in hand, we can move on to design, we can move on to implementation, and then we can begin doing verification. And with verification, what we're essentially asking ourselves is, did the software that we build actually satisfy all those requirements? And then once we've convinced ourselves that that's the case, we move on to validation. And we can ask ourselves, did this set of requirements that I come up with actually result in a piece of software that's both correct and useful? So that example is fairly, as I said, formal. It's fairly heavy. You get this sense that there are these different phases of the process, and you need to finish one before you move on to the next. And oftentimes, that's probably not going to be the case in this particular community. So I've come up with a different workflow where we're doing something that's more incremental and iterative. And the idea is that we're just going to develop in little incremental steps, and every step we're going to do some mixture or some combination of what we just saw in that previous workflow. So at one particular increment, what we can do is look at the requirements that we presently have, as we presently understand them. And we can do some elicitation, specification, and validation to try to improve those or to extend those. And once we've got that in hand, we can, as a group, sit down and try to identify what are the next necessary and high priority tasks that we want to undertake. So we do those, we design, implement, and verify those, and then we move on to the next increment. One of the things that we have to be careful about when we work in this iterative way is that oftentimes these tasks, well, in some cases, they might be very local. They're just on one part of the code. And if we're not careful, as we go through these different increments, just looking at one tiny little bit of the code, we might end up getting tunnel vision. And so what we've done locally is great, but we might be missing this global structure that we need to build into the software. In other words, through this process, there is some possibility of degradation. So you want to build into this workflow the idea that people should feel free and be happy to simplify and improve the code to try to combat that natural degradation that could potentially occur. So an example of how we can do requirement elicitation is through something called user stories. The idea is that when people are going to get together and they're going to do this elicitation, we want them to be able to express to each other what it is that they think the software should do, what constraints should be put on the software, and why that's important. And so we'll ask them to do that in the form of a statement that has a particular pattern. So one common pattern is as a blank, I would like blank, so that blank. And the idea is that when these people share these user stories, that should ignite this sort of nice, rich conversation, this discussion, so that people start understanding each other and try to come to this common understanding of what it is that they want to achieve. So an example of a user story is, as a user of the software, I would like the storage of data to make good use of HPC resources and to leverage pre-existing libraries for reading data so that my simulations run in less time and the time to results is decreased. So when this person presents this user, I'm imagining that people are going to start to ask them simple questions like, what does data mean to you? What does HPC resources mean to you? And we can imagine, for instance, that different people are going to have a different understanding of what it means to leverage these pre-existing libraries. So through these questions and these answers, we're going to hope that this team comes up with this first version of a requirement. The software shall record simulation results, configuration values, hardware information, and telemetry via parallel I/O library and using a standard file format. So the idea is here, we now understand what data means to this person, and we understand what HPC resource is. But we can also imagine that there's someone that's a little bit unhappy about this wishy-washy term standard. They might not really know what that means. It might be ill-defined. And so through some more discussions, they might find out that this person just wants to be able to get access to that data quickly using Python, R, and let's say C libraries. And so they arrive at this improved lower level specification. And then we can also say that at some point someone just says, like, look, if we can go lower level and constrain ourselves to using this particular library at this version or greater, then this person's going to have all of their desires satisfied. So when we talk about requirements, we use words like we're going to gather the requirements, we're going to discover the requirements, or we're going to come to an understanding of what the requirements are. And I think this language is very purposeful and actually reflects the process. The idea is that when we start out on a design project, we all have within us some general idea of what it is that we want to do. However, we don't understand it quite well yet, and we're certainly not in a position where we can communicate about it in an effective way. So what we're going to do is work with these refinements. We're going to constantly be refining them, and as we do that, we're going to start iterating and improving our understanding of what we do until we sort of start to get close enough to converging to this ground truth that we seem to have inside of ourselves. So one way for this sort of work to proceed in terms of refinement is through these type of spiral processes. So here I've got, again, a large formal process where we can imagine that each iteration through the spiral, we're going to be adding on another layer of requirements. So we could start off with the software science requirements. We do some elicitation and specification of those. And then we can do a feasibility study of these to determine whether or not those science requirements are something that we can actually achieve with our resources. And then we take the experience of that, we feed that back in to improve our requirements, and we add on user requirements. We do some specification and elicitation again, and then we can start doing some prototyping. We take the lessons learned from that, feed those back in again, add on some technical requirements, and by the end, as we go through the spiral, hopefully we will have converged on a reasonably sufficient and decent set of requirements. And then we can do that validation that we need to do. If we want to do something that's a little bit more exploratory, maybe we start out by just specifying the requirements that we currently understand or that we think are the most important to try to understand up front. We could do some elicitation specification of those again, do some lightweight prototyping, use those to improve that initial understanding, then do some more full-featured prototyping, and then again we feed those back in until finally we get to that nice set of requirements that we think are reasonable. So as drawn here, I don't want to give the impression that this is something that you would do in a week or a month. It's just one monolithic process. This could very well be something that you're just continuously doing throughout your entire process of design and implementation. So what happens oftentimes when you do these elicitation sessions is you're going to get very busy people together. These people have a great deal of expertise in one shape or form, and they're going to dedicate this time to really hashing out these details and doing this rich brainstorming. And so one of the main byproducts of this is that you're really going to be generating a great deal of knowledge and understanding, and we don't want that to just drift off with time. We would like to actually try to encode this in some way, and so we need to do some sort of documentation. And again, I think this was related to a little bit of what Catherine was saying. One part of requirements could actually be determining what your assumptions are and therefore documenting in this particular way. So documentation, we want it to be clear, we want it to be readable by many different people, and we want it to be living, which means that as our understanding of what it is that we're trying to achieve evolves, we need to co-evolve the documents with those, which means that we need to do maintenance, unfortunately. In order to make that something that really gets done, of course, it would be ideal if it's both simple and easy. So we can start to ask ourselves, how can we try to do this documentation? So if I've got requirements that are somehow being imposed at a lower level, at the level of a function or class, I can try to find some way to document those requirements within the comments and the inline documentations. However, there will likely be higher level or more broad requirements that potentially don't fit in that type of a documentation. So how do we deal with that? With those higher level? Do we go a traditional route and have a couple of dedicated traditional living documents? Do we try to put them into a user's guide and or developer's guide? Or do we try to realize that, look, when I did these requirements, I actually came up with a test case, and I'm actually going to program those. So to some degree, the test cases function as some level of documentation. So as long as I have those, and I've documented those, maybe I've done a reasonable enough job of writing this down. So we'll go over the good, the bad, and the ugly of requirements. So the bad and the ugly is that I think oftentimes people don't think that they need to write down the requirements because they think it's already obvious and there's no point to it. However, the reality is when you try to do this, it's actually extraordinarily challenging and frustrating. Oftentimes, some people will find that this is just an impediment to direct an immediate progress which they would like to have. And as I've mentioned, requirements, the reality is that they're going to change. So there's a couple different reasons why the environment might be changing. So one might be because, as Catherine said, suddenly your platforms have become more challenging, more complex, and more heterogeneous. Another reason might be that your software is simply existing in a very competitive environment. So if I spend too much time doing requirements, by the time I've actually written the software to satisfy those, my software is now no longer competitive or useful. Right? That's another reason. But another reason, I think oftentimes we have to be honest with ourselves, is that simply it has nothing to do with the requirements actually changing. It has to do with our understanding of what it is that we're trying to do is actually changing. And that's natural, and it's also reasonable. So the final challenge is it's hard to know when enough is enough. So if you really try to push for a complete set, you're probably just wasting your time, and it's probably going to be a demoralizing process. If you go too light, though, you're going to end up having sort of gaps in your understanding. You're not going to understand all of the constraints. And therefore, you might end up getting too deep into the implementation phase and suddenly finding out that some of the software that you've written is going to be really hard or really costly to try to fix to get it to do what it needs to do. So the good is that for me, requirements is really about achieving clarity, a common clarity. So we want to arrive at a clear and shared understanding of what needs to be done. We're going to do that by really coming up with a strong set of definitions and concepts that are shared by all. And we want to, in some cases, we can imagine there will be people who really have been working on this particular topic for a lot of time. So they have a lot of good requirements and ideas that are in their head, and they're not even going to take the time to share them because they seem so obvious to them. However, the rest of the team might not even think about these requirements. Right? And so through this process of requirements, we hope that those obvious ideas actually come out and are shared with the group. And so principally what we're also doing, and I think this is important as our teams become more interdisciplinary, is that these requirements are going to be able to bridge the gap between differences in disciplines as well as differing levels of expertise. And also very importantly for me as the requirements, we're going to be linking them with the actual verification. So that thinking about verification becomes an upfront process. So you've heard me use terms like formal and exploratory. There are more formal definitions related to that sort of stuff. So on one end of the extreme, you have plan-based development, which puts more importance on upfront effort to really arrive at this clear shared understanding. It can be a little bit more formal, structured, and rigid, so it has more overheads. For certain type of software, like let's say mission critical or life critical, that might actually be important. In other cases, it might not be. On the other end of the spectrum, then, we have agile development, where we're really going to be continually evolving our design and our understanding of what it is that we're doing as we're working through implementation. The idea here is that they acknowledge the requirements are constantly changing, and they want to really bake that into the way that we work. I think the terms plan-based and agile can oftentimes be very polarizing. So as I learn more about these and you go online, you see people really just getting into angry screeds about this. And so I found this one particular quote in Ian Somerville's book on software engineering. He says, software developers should be pragmatic and should choose those methods that are most effective for the type of system being developed, whether or not these are labeled agile or plan-based, right? There is this pure agile model, but also, as we heard Catherine say, that's perhaps a good way to go with CSE projects, but oftentimes people aren't following that exactly, and they shouldn't feel the need to. They should adopt what's good for their particular project. And so one area that this could be is if you've got this infrastructure, this extensible framework that you want to put into the software, it might really be that the requirements associated with those are actually static. They're not going to change significantly over a reasonable amount of time. And so maybe we want to put a bit more upfront effort, use something that's more close to plan-based there so that we really end up with a nice mature interface for that is extensible. Whereas, as Catherine also mentioned, if we're working on the software side, the mathematical models, let's say the physics side, where we can't possibly think about writing down the requirements in any stable way, then maybe that's where Agile becomes a really great way to go. So any questions at this point about requirements? Or should I push right on to TDD? Nothing? All right. So when we start doing development of software, oftentimes we have these lofty aspirations. We want to write correct code. We want to do so productively. What's more, we want to be able to convince ourselves and others that what we've written is actually correct. We also want to have the code written cleanly and maintainable, and we want to have a nice set of useful documentations that we maintain up to date. However, the reality of the development is oftentimes we come up with dirty code that's really in a prototype form. There's no little or out-of-date documentation. And the testing that we've done might not actually be up to our level of what we would want to do given more time and effort. So the idea is that test-driven development, or TDD, is a method that we can use to try to achieve those lofty goals. And hopefully, if we use them, it should also make the process of doing testing and documentation a little less tedious, let's say. So TDD came from extreme programming, and it could be classified as an agile software development method. The fundamental idea is that we're going to co-evolve co-evolve the development of code at the same time that we write the automated test that we're going to use to verify the functionality of that same bit of code. The spirit of this is not to sit down and try to write the perfect implementation up front. The idea is to just write the quickest, easiest brute force code that you can get away with to just get your tests passing, and then go back and refactor that implementation at a later date using those actual tests. So this is a fairly complicated workflow that I've come up with that fits a little bit with the example we're going to go through shortly. If you go online, you'll see that there are multiple different workflows for TDD, but essentially it's all about this. You'll usually find the statement red, green, refactor, and we'll come to an understanding of what that is as we work through the workflow. So what you're going to do when you start out is you're going to sit down as a team and you're going to try to identify what is the functionality that's needed today or in the near future. TDD does not advocate that you try to use this process to try to write software that you think might be useful in 2 years' time. Right? It's really about what you need today. And once you've come to a reasonable understanding of what that functionality is, you can sit down and start to think about how you're going to verify that, how you're going to identify tests to cover that functionality. And so hopefully this should start to sound fairly familiar, right? This is all about requirements to some degree, analogous to it at the very least. The idea is we put up a little bit of upfront effort in here to try to really understand what it is that we want to do and how we're going to check it, and then we start implementing. So once I've done this, we have some tests. I'm going to write this first single test, and I'm going to run that test, and I'm going to see that it fails. It should fail because I haven't written any software yet. That's important. That's the red, right? Because what we're doing with that is we're confirming that this test is actually functioning. It's capturing this failure that it's set out to discover. So that's really an important step. Once we've done that, then we start writing code to pass just that test and the previous test that I might have already written. So once I do that, then I run the test that I've presently got, and I see that those pass. That's the green. So I want to see it go from red to green, right? Once we go through these different steps, we're satisfied that we wrote the minimal amount of code we need to pass our current test. We might want to actually stop for a second and ask ourselves, is this dirty implementation that I've gotten right now becoming a little bit too much of a burden? For instance, maybe it's taking forever to run right now. If so, maybe you can stop and go back and refactor that implementation a little bit. And you've got those tests that you've already written to actually aid in that process of the refactoring, which is wonderful. And so after you're done with the optional refactoring, you ask yourselves, are there more tests to implement to cover this functionality? If so, you go back and you start implementing on a test-by-test basis with this red-green refactor until you're done. So for the example that we're going to go to, I've come up with this augmented TDD. This is not a thing. This is just something I made for this talk. The idea is that when we do this process of identifying the functionality and identifying the tests, let's actually just start writing some of the documentation at the same time. So for instance, the inline documentation. In other words, we're discovering these requirements, we're discovering these constraints. Let's just write them down up front in terms of this nice documentation that hopefully will be useful for other people. And then, of course, as we go through this process of implementing, we're going to be learning about what it is that we're trying to do, so we update the documentations at the same time. So fundamentally, this is something I try to do. I really like this a lot. The general experience I have is that if I can't express what I'm trying to do in my own native language or a human language in words, then I'm probably not ready yet to try to express it in the form of code. So the example we're going to do is the Fibonacci sequence, nice and simple, right? And so the first thing that I'm going to do is really establish a contract. I'm writing a function called Fibonacci. It has this input parameter. It has this output. So I establish that in terms of a function declaration, and I return this silly value. And at the same time, I'm adding on that inline documentation. So through that function declaration and through that documentation, I am establishing a contract with the people who are going to be using this function. If you give me these inputs, these are the outputs that I'm going to give you. These are the input, and these are the corner cases and the edge cases. If you give me inputs that put me in that state, this is going to be the output, right? I'm establishing a contract with the client code. And so what I have here is this routine shall calculate the nth number in the famous Fibonacci sequence, which is defined recursively as blah. It takes an input, which is the index of the desired element in the sequence, and it returns that element. So at this point, people might be sort of angry with me because that definition I put up is not sufficient, right? It needs two starting parameters to prime that recursive sequence. And when I went online, I found out that there were actually two different definitions for the Fibonacci sequence, at least two. So the first one is you can have f0 is 0 and f1 is equal to 1. And the other one is f1 is equal to f2 is equal to 1. So this difference is actually fairly trivial. But nonetheless, we have to make a decision. This is our first design decision. So rather than just choosing something arbitrarily, we'll put a little bit of thought into this. So up front, on the top there, I have my really nasty interface that I just got out onto the paper, right? It was just there. And so we'll see that immediately there's some things that I really did that were silly. So for instance, we're using integers. Whereas according to those two definitions, my input can only be either a positive integer or a non-negative integer. So we'll change that to an unsigned int. And we also recognize that the output is going to always be positive or non-negative. So we'll make that change as well. And now when I sit down and I thought about this, the fact that I changed this over to unsigned int made me realize that on this particular case, someone could give me n is equal to 0, which is not a valid index for this sequence, which means I'm going to have to do some sort of error correction. Whereas with this one, I don't need to handle that. Any possible index that you give me is valid, which seems nice. However, in the back of my mind, I'm also thinking that I'm going to program this up in the recursive case from the very beginning. And I start to realize that at the end of the recursion, I'm always going to be adding 0 to 1, which seems sort of stupid and wasteful. But nonetheless, I chose this interface 1. And so what I did then was go back to this contract that I made in terms of the function declaration, in terms of the documentation string. I now need to update it. So I added in this f0 is equal to 0 and this f1 is equal to 1. And that's all I had to do. And so this was actually fairly interesting. Because at this point, because I don't have these error conditions, because all of my possible inputs that you give me are valid, my documentation was actually fairly simple, compact, easy for me to write, and hopefully easy for people to read. And so once we've got this, and again, I point out there's no error correction, now we're going to start writing tests, right? And I emphasize again, we want to see this test fail. So I wrote just simply two tests here on the right. So I'm going to get the Fibonacci elements for the 0th and the first element, and I'm going to check that those have the values that I expect. And when I look over at what I currently have written for this software, one of those should pass and one of those should fail, right? So I run that, lo and behold, one of two tests passed. I get that red that I was looking for. This test is actually detecting a failure, which is great. So now we need to start writing some code. Again, the simplest and easiest code just to pass those two tests. So all I did was add in n less than 2, then return n. And when I run those tests, lo and behold, I'm green. So I went from red to green. That's great. That work that I did was perfect. However, obviously we know that this code is not yet fully written, and the way we know that is that our test suite is currently deficient, right? It just doesn't have enough tests in it to be able to confirm that it's working. So then we're going to be destructive, and we put in 3 tests that we know should fail. So we ask for the 2nd, the 3rd, and the 6th elements in the series, and we run that. Just 2 out of 5 tests are passing exactly as we expected, so we're back to red. We like that. We're happy. And so now I can go through, and I'm just going to add in this one line where I use the recursive formulation. And when I run those tests, all of them are passing. So I'm back to green. I'm happy now. This seems like a fairly reasonable set of tests. I think that what I've written is actually functioning correctly, right? So now what I can do is actually stop. And I can say, am I happy with this dirty brute force implementation that I went with? It's nice, it's compact, but maybe it might not be performant, let's say. So I want to refactor that. I'm not going to change that contract. The documentation that I wrote in terms of requirements is still valid. That interface of the function is still valid. All I'm going to do is, behind that interface, change the implementation by going to an iterative method for determining those sequences. And so when I rerun the test, I'm going to find out that those all pass. And what you'll see is that this is more lines of code. This actually took a little bit more thought for me to come up with, and compared to the recursive version, which was interesting because I did it quickly. I got out the easiest way to do it. I built up those tests. Now that I have those tests running, I can actually do this implementation and rewrite the implementation in a more performant, potentially, but more difficult way. They help me to do that, right? So test-driven development, what we're doing here is incremental development by writing and modifying the code, and at the same time getting immediate feedback using those tests that we just wrote to determine if that code we wrote actually does what it's supposed to. We're co-evolving the functionality of the code along with determining that, let's see, where am I? Co-evolve the functionality of the code with the verification of that functionality, right? That's important. And as you see then, what we're also doing therefore is something analogous to requirements analysis and verification planning. What's really great about TDD is that by definition, you're only coding up code that is actually needed in today or in the near future. And also by definition, that code is always testable. So if people are working with legacy code that was developed without tests, I imagine that you can appreciate that sometimes you come across some beast of a function that you cannot possibly put a test on. Or if you manage to do that, the fact that it's failing is not actually useful because it's not going to help you to either refactor that code or to actually determine where the bug is. So this is a really great byproduct of TDD. Of course, we're also getting out this proven test suite, which we can use in the future. And a point that you might not have appreciated yet is that hopefully this really does minimize the tedium of writing tests and writing documentation if you go for that augmented one. The idea is that if we put off the documentation and writing the test to this last effort, we're going to have this horrible sufferfest of a month where we're trying to do this tedious stuff. What TDD is saying is break up that tedious work into little tiny palatable chunks and intermix that with the interesting part of the development process. So hopefully you'll get better products with less suffering. And also I want to point out that very importantly, what TDD is doing for you is potentially moving you to a different operational mode where you're going to be proactively preventing the injection of bugs into your code. You're going to find that bug that you wrote or that bad line of code immediately and fix it. This is in opposition to being in a reactive mode where you're simply waiting for people to create bug issues and then trying to go track those down some months or years after that bug was created. And again, this idea of not fixing yourself to plan-based or agile, this is sort of an agile method. But if your project needs to go a little bit away from agile, there's no reason, for instance, why you couldn't potentially use this, right? Pick what works for you. And then I've got some bibliographies interspersed that you guys can feel free to get more information on if you would like. So at that point, I'm done with TDD and requirements. Does anyone have any questions? No? Everyone's ready for the break? I've got a quick question. Okay, yeah?
So it seems like one key feature here is getting that immediate feedback from the test suite.
I'm sorry, can you say that again?
Sorry, so it's pretty important to get that immediate feedback from your test suite.
Yeah.
So do you have suggestions for avoiding a bloated test suite and long run times of the tests themselves?
So I think like when you read TDD, I think what they say is, I mean, we'll have to put into context, but what they're saying is that you just need to write the amount of tests that you need to have confidence in what you're doing, right? You're writing the code, you get some idea of probably where the bugs are occurring and where they're not, and so you try to put the coverage there. I mean, you're right. I mean, if you try to put a line of code, test for every single possible path through your code, every single line, you're just going to get mired down, and you're going to have this beast of code that you can't possibly maintain in the future, right? So there's going to be a balance point here. We'll talk about this a little bit in terms of code coverage. But I do, like I said, I want to put this in context. I think I haven't read these books for a number of years, but if I remember correctly, it was always you don't need to test everything, but they're operating under the assumption that this is more of an industrial environment where there is a dedicated test team that's sort of cleaning up. So if you don't have that, then again, that's going to put a little bit more pressure on you to write a few more tests.
So essentially you're saying that anticipate where you have, most likely have bugs and good tests for those.
Yeah, I think that
software where you know that probably this function is where it's likely to screw up.
I mean, you're going to get an idea when you're implementing things, right? Like, I'm putting a lot more thought into this, right? Or you're going to get this feeling that, oh, I'm having to be too creative here, right? There's something going on at this point, so I'm going to try to be a little bit careful there. What you also might find out is you do that brute force implementation where you probably little likelihood of having a bug. But when you start to implement, you try to refactor it to re-implement it in the final form that you want. There, you might find out that some of the tests that you originally wrote don't cover the weaknesses now that you're discovering. So it really is going to become sort of this really dynamic process, right? Listening to your gut to some degree, right? Do people use TDD in here? Yeah, we've got a couple people. I think I started learning about this like 2012, and I love it. I can say that one of the unhappy side effects of this is for a number of years I was in this coding mode where I was just always developing things, and so I could use TDD. My ability to use a debugger completely atrophied because my code, I didn't have to come back and find hard bugs at a later date. It just didn't happen. So that's not likely going to happen to us, right? We've got pre-existing code, but you can, at a certain point, you want to add on a new feature. You can use TDD for just that new feature, right? It doesn't have to be for designing an entire piece of code. Yes.
What strategies can you take if you have some sort of large piece of code that's sort of hard to verify individual, very small aspects of?
Okay, so I'm going to let Anshu. She's going to cover that at a later date.
There in the next presentation.
Yeah. So she'll get into that because that is a very difficult issue, isn't it? Yeah. Yes.
So at the beginning in the design process, you said that you should write the simplest implementation of the code you know.
Yeah.
But then in the Fibonacci sequence, you chose recursion instead of the for loop. So when do you choose the better implementation to start your test suite with? At what level?
Again, that's up to you. I mean, the idea is once you get that test suite up and running, that's extraordinarily useful, and it's going to help everything else that comes afterwards. So just take whatever steps you need to do to get that reasonable test set under design and actually working. So oftentimes I find that conceiving of the test cases is really the hardest part, right? So some of this is you're not even going to be able to sit down and know a priori what are the tests. You're going to have to battle with that a little bit. And so then you just keep doing that. You just keep adding on more and more tests. So write the code to just get those tests out, right? And then hopefully that will give you some level of clarity. So for some people, maybe they don't like recursion, and maybe the iterative way would have been the way for them to start, and that's perfectly ideal, right? And you might get, at some point, like when I run these test-driven development or the test suites that I've developed, if they're quick enough, I always get a little number out that tells me how fast the whole test suite executed in. And after a while, I saw that originally I was running in 5 minutes. Now it's 30 seconds. So I'm getting some sort of profiling very quickly to figure out now that I need to re-implement things, or we need to re-implement certain aspects. But you also might be shocked sometimes because you might run something that's stupid and brute force and then find out that it's actually perfectly fine and doesn't need to be rewritten, which would be a wonderful surprise, I think. Any other questions? Okay, so the TDD was a lot more exciting than the requirements part, huh? Requirements can be kind of dull, but they're powerful. Okay, so I think we're ready for break time, I imagine. We lost Marta, but I think we can make that executive decision, can't we?